Hello everyone, today we'll talk about the problem second minimum time to reach destination. We're given an undirected, connected graph. We want to get from the first vertex to the last vertex. But we're interested not in the minimal distance from the first vertex to the last vertex, but the second minimal distance. So, among all the possible paths from the first vertex to the last vertex, we want to return the length that's the smallest, but not equal to the smallest possible length. Because normally when you would, for instance, look for the second shortest path, you would possibly find that there are many ways to get the same distance as the shortest path, and we're not interested in that here. We're interested in if the shortest path is, let's say, 8, and it's possible to do a 9, then we want to return 9, even if there are many ways to get to that vertex in 8 steps. And also another difficulty is that there are some traffic lights, and traversing an edge takes some time. And in order to traverse an edge, you first have to wait for the light to turn green, or if it's green, then you can go immediately. And then, of course, you traverse an edge, which takes some time. And then at the next vertex, if you want to go further, then you have to wait for the green light. And you cannot wait in a vertex and not do anything. You always have to move, if possible, whenever a light turns green, to another vertex. So the problem is pretty contrived. One thing we can focus on first is the fact that time it takes to traverse an edge, and also a time it takes for the traffic lights to change from green to red, red to green. Those are both just integers. So every edge has the same cost, and also those traffic lights are all changing simultaneously. Now typically when edges have the same length, then we can forget about that length and maybe adjust the result at the end. And also here, since all the traffic lights changed at the same time, we can probably also forget about them changing, because if we know the number of steps we've taken, we know exactly what time it currently is. So this is just something that we can forget and adjust our result at the end. Which means that we're just left with a graph, and you want to find the value of the shortest path that's not as short as the real shortest path from the first to the last vertex. And I'd say two basic ideas, since we can visit nodes twice or multiple times, is that when we have a shortest path from the first to the last vertex, then the answer can be easily that length of the shortest path plus 2. Because we can just go one step backward and then again forward along the path. We'll have a path that's twice as long, and that will be the answer. And the only other possibility then is that the second shortest path, as defined in this problem, is a single step longer. And there is a way to just implement it in such a way that we can look at all the nodes that are reachable in exactly the same number of steps as the final vertex. And if we can reach the final vertex from those vertices, then indeed the second shortest path is n plus 1, otherwise it's n plus 2. But it's not the solution that I'm going to talk about here. Instead, what we can do when we're interested in the second smallest value is just to maintain both the shortest distance and the second shortest distance. So we'll visit every vertex twice. And we'll be doing it since, of course, all the edges have the same lengths. We can use a simple BFS. And in general, whenever you have either all the edges the same length, or all the edges the same length and some edges of weight 0, then you can use a BFS. So we create a graph in a standard way. We want adjacency lists. And instead of just having the distance from each vertex, we'll have two distances. The distance for the first visit and the distance for the second visit. Start at vertex 0, and it's our first visit. We keep a queue. In Python, of course, we use a deck. And we just go through all the vertices. We take the current vertex that's in the front of our queue, and that vertex allows us to reach all its neighbors in one step more than the distance that we have taken to go to this vertex. So this is either a first or second visit in that vertex, so we take the appropriate distance, which is just something that we remember on the queue. And now for our neighbors. If the distance at 0 is none, that means that this is the first time we can even reach that vertex. And in that case, we just take its distance for first visit to be equal to the distance that we can give when looking at the vertex we're currently at. We add it to the queue. Otherwise, we do the same with the second visit. And remember the second visit. Only, of course, if we haven't visited it a second time. And also another important condition here is that the distance has to be greater than the distance of the first visit. That's because of this specific definition that we've had here, that we're not interested, when it looks at the second minimum value, not interested at the length of the second shortest path, but the length of the shortest path of those paths that are longer than the real shortest path. So this allows us to skip all the possible other ways to get to the vertex in the shortest amount of steps. And after that, in dists, we'll have calculated the number of steps, the shortest amount of steps to go from the starting vertex to every vertex, and the shortest number of steps to go a second, so the shortest, the second minimum value. The shortest that's not equal to the real shortest. And now we can just simulate going through the graph and taking into account the time and change. We start with all the lights green, and now lights are red if when we divide our current time by the time it takes to change the light, we get an odd value. In that case, we have a red light, then you have to wait, and you have to wait until we again are divisible by change. One way to do it is just to, since currently there is some remainder, when we divide the time by this period of change, we can just make sure that we add the remaining portion of the value of change to our current time. So for instance, if change is 10, res modulo change is 3, so we want to add 7, and this is what we do here. There are other ways, of course, of implementing it. Then we take the time to go along an edge, and we remember that we've taken one more step. And we need that because we want to take exactly the number of steps that the second distance to the last vertex requires. And at the end, we just return the result.